Welcome everybody. Like Melanie said, I'm Lucas. I work here in Booking, so very happy to see you all here in my own territory, so to speak. And today I wanted to talk about diagnosing statistical and machine learning models. I've been trying to put up this presentation for a while, and I thought that the best way to put it is with examples. So I prepared 2 examples today. So let's get started with the first one, which is about bicycles. So if you were expecting to see some hotels, well, remember in Amsterdam, bicycles always have priority. Ask the owner of this car here otherwise. Okay, so the idea is to study a system about bicycles rental. And this is a system that allows you to rent bicycles, and we want to understand the demand. So the data we have is about how many bicycles are rented per hour. And we have information about the weather. In particular, we have temperature, the speed of the wind, the humidity, the overall weather situation like cloudy, sunny, or rainy. And we have some information about the time, whether it's a weekday, whether it's a holiday, and all the obvious features you can expect from a date, like the month, the season, and stuff like that. This is 2 years data, so it's about 17,000 observations. Not big, not small. And the purpose is explanatory. So the idea is to understand which of these variables impact the demand of bicycles. And we also want to know, to quantify this influence of these variables in the demand of bicycles. And the model is a linear model, and the algorithm is ordinary least squares. I implemented this using stats models, scikit-learn, pandas, the usual suspects. And let's see what happens if we just throw this data to OLS in stats models. And we get the first undesired behavior, which is a lot of non-significant coefficients. So this is a linear model. And what you see here in the x-axis are all the features I'm using. Only a few are labeled, of course. And the y-axis, you see the p-value for a t-test for correlation of the input variable with the output variable. So essentially what this means is that the model fails to find significant correlation between the input variables and the target variable, which in this case is the amount of bicycles rented per hour. Related to these large p-values, of course, we see very large standard errors. So here in the x-axis you can see again the feature names, and on the y-axis you can see the relative standard error. That is the standard error divided by the actual estimated coefficient. And you can see it goes all the ways from a little bit less than 10% to 60%. That is the level of uncertainty we have about the coefficients of these variables is really high. And this is very bad because then it means we cannot really establish relationship between these variables. And that's exactly the purpose of our model. Now, there are several reasons why this may happen. And this is, in a sense, 2 symptoms of a very common issue in machine learning and statistical modeling, which is large variance when estimating coefficients. If I didn't put the chart, but if I change the sample, and the columns and the rows, we can see how the coefficients actually change a lot. And that means, pretty much this is the literal definition of overfitting. The values that we estimate, that the algorithm learns, are very much coupled with the data that we use to estimate them. So one reason for large variance is a bad relationship between the amount of observations that we have and the amount of parameters that we want to estimate. Now in this case we have only 40 variables. So this means a linear model will need 41 parameters, including the intercept. And as I said, we have 17,000 observations. So if you want to estimate 41 parameters with 17,000 observations, it's just fine. It should be okay. So we can definitely discard the issue of not having enough sample size. Now, what's another pathology that can produce these symptoms? Well, there is one that is quite common, which is known as multicollinearity. And the idea of multicollinearity is that if we take input variables, at least one can be predicted by looking at the others. So in this case, for example, we have the temperature. So maybe we can predict temperature as a linear combination of humidity and the speed of the wind. If that is the case, then that means that there is redundancy in the variables that we are using to predict or to estimate demand. And this redundancy completely, prevents us from making conclusions about how these variables are related. Because algorithms like ordinary least squares and pretty much every linear algorithm, even SVM with a linear kernel, will try to explain the variance in the target variable, in this case hourly demand of bicycles, by assigning coefficients to the input variables, to independent variables. But if there is redundancy in the independent variables, then these coefficients can be assigned arbitrarily. And this arbitrary assignment of coefficients actually comes from the fact that there is redundancy. And that makes these values, which is the thing that we really care about, really depending on the data that we are using. And that's why we see large variance. We change the data and the coefficients change. So this is a nice hypothesis, but we need to make sure that this is the case in our model. Is there or there isn't multicollinearity? There are many ways to check for multicollinearity. Most statistical packages give very good estimates and hypothesis tests of multicollinearity. Stats models has a thing called the condition number, which is quite a tongue twister. I'm not going to go into details. And the main reason why I think it's not very important is because these tests only tell you that there is multicollinearity, but doesn't help. They don't help you at all to understand where this collinearity or multicollinearity is coming from. It doesn't give you information about how to fix it. So what I use usually in the past, actually not so much these days, and I propose is to use what I call a clustered correlation plot. And the idea of the clustered correlation plot is quite simple. It's just take the correlation matrix of your input variables, take the absolute value. We don't care about the direction of the correlation. We only care about whether there is or not correlation. And then apply a clustering algorithm to this matrix. And the objects we're clustering are the variables. And for this, it's recommended to use an algorithm, a clustering algorithm that doesn't require the amount of clusters beforehand, because of course we have no idea. And the very nice one that I successfully used in the past is affinity propagation. Back in the days, I was using my own implementation. Today, scikit-learn has a very nice implementation of affinity propagation. So you can just throw the correlation matrix to the implementation of scikit-learn and get the results. Once we have the clusters, we can plot the correlation matrix, but sorted by cluster assignment. So in the rows, we're going to put first all the variables that are assigned to the same cluster, then the variables that are assigned to the second cluster, and so on. So if we have a perfect system where there is no redundancy at all between the variables, no correlation at all, we would see something like this. So the diagonal is absolutely red. This is because there is always absolute correlation between every variable and itself. This sounds something that is good to check. And then off the diagonal, we see blue, in this case, a deep blue, a very dark blue, because it's zero, because there's no correlation whatsoever with in between any other variable. Now, if we apply this technique to the bicycles data set, this is what we see. And we can see several things. First of all, there's blue all over the place. That's a good thing. There is information in pretty much every variable. But we also see, of course, the diagonal red, which is very important. But we see red, orange, green, yellow everywhere off the diagonal. And that means there might be some issues with multicollinearity. And we also see the clusters that the algorithm found. And for example, you have holiday, weekday, and working day. That seems to be a pretty good cluster. Hour, humidity, and wind speed is another cluster. Maybe it doesn't make that much sense. But then we find, for example, the third cluster. It's cloudy, sunny, snowy, and rainy. And they are all together in the same cluster. So let's dig deeper into that one. So what we see here is that cloudy is highly correlated to sunny. And cloudy is slightly correlated to snowy. But we also see that rainy is not really correlated to any other of the variables. But the affinity propagation algorithm still manages to capture these 4 variables in the same cluster. And this is telling us that there is a problem with these 4 variables. Now, what is the problem? Well, this one is quite obvious. We have 4 categories. And every hour there is exactly 1 category. So there's only 1 weather situation per hour. And I use one hot encoding using 4 binary variables. So if you do that, then that means the sum of all these binary variables will always be 1. And that means I can always predict one of the binary variables as the sum of the others, or 1 minus the sum of the others. And this is exactly the definition of perfect multicollinearity. I can perfectly say, look, it's not cloudy, it's not sunny, it's not snowy, it's got to be rainy. It's cloudy, then it cannot be rainy. I can always predict one variable looking at the others. And this introduces this pathology known as perfect multicollinearity. So this I got using pandas, get dummies in this case, if we want to look at some code, and you specify the categorical feature that you want to one-hot encode. And by default, pandas won't drop any variable or anything. So the way to fix it is very simple. We ask pandas to drop the first level. In this case, I think it will drop sunny, because it's the first that is observed in the dataset. This will fix the problem, but once we do this, we need to be careful about the way we interpret the coefficients. Because once we drop one categorical level, then the coefficients that we estimate for all the other categories will be with respect to the one we dropped. So suppose that we drop cloudy here, and then we observe that sunny gets 10 more bicycle rentals. That is, sunny gives you 10 more bicycle rentals with respect to cloudy days. And this is very tricky and it's very important to take care of. And when we have small categories, small amount of categories like this, it's easy. But if we have plenty, like cities, like countries, and whatnot, or hotel IDs, then the interpretation of the coefficients gets much more tricky. Okay, so of course this is a problem for every categorical variable in the set, so I fix it for all of them, and you may think that will fix the whole problem. But if I repeat this p-value on all variables, we see that we improved a lot, but not really done. We are far from done. There are still many variables that show large p-values, and that means we still are failing at making conclusions, which is in the end the purpose of our model. So if we repeat the process, here's the second clustered correlation plot. And here we can see that there are less clusters, there is less red. That means by dropping the first level of every category, we improve clearly. The first cluster seems to be fine, but the second cluster seems there is a very dark red spot. And then that might mean that there is something wrong over there. So let's dig deeper there. First of all, the cluster is quite consistent. It's a summer temperature, a temperature, September, August, July, June, and February. These are variables that make sense to be clustered together. Now, it's important to know that as we go fixing this multicollinearity problem, the clusters will lose sense, right? Because the clustering tries to find correlated things, and if we remove them, then the cluster will lose cohesion. So what we see here is clear. Is temperature is very highly correlated with this suspiciously named A temp. And by this moment, I decided to go and read the documentation of the dataset. And as it turns out, the temperature is the temperature, what you would expect, and A temp is the filling temperature. And of course, these two variables are highly correlated, are absolutely redundant. So it's quite a no-brainer that we need to drop one of them. Now, let me comment just really quick that this is not always the case. Sometimes it's really difficult to choose a variable to drop. And there are techniques that we can use to avoid that. For example, taking the ratio of the variables is a trick that works very well. If someone is interested, I can take it offline and have examples. But I couldn't find it in this particular data set. Just to want to make the point that removing variables is not always the best solution. Okay, maybe we're done. Well, not really. We repeat again the cluster correlation plot, and we see again that there are some yellow, greenish clusters off the diagonal. And it's funny to see that rainy is alone there. It's its own cluster. I'm not sure what that means. But yes. So if we look at, by the way, this is Washington. This is not Amsterdam. I got you all. So if we look at these clusters that are showing some not so healthy structure, we're going to look at them all together because they are all related. So in the first cluster, we see summer is correlated with summer, August, A temp, that's good, and July and September. Then we also see that fall is correlated to October and November, and we also see that spring is slightly correlated to June, and a little bit more with May and April. So what this is telling us is very obvious, actually. It's not shocking that the season is correlated with the month. But this shows actually a nice ability of this clustered correlation plot of picking up correlations between multiple variables. And this correlation is tricky because it's a hierarchical structure. If we know the month, of course, we can tell the season. But if we know the season, we don't definitely not know the month. We just get some information. And this means that this tool is really helpful to find more complex multicollinearity structures or multicollinear structures in the dataset. And again, in this case, it's very easy to solve. We can just drop one of the variables. And in this case, I chose to drop season because there are only 12 months, and we have a lot of data to estimate properly a coefficient for every month. If we would get, for example, and this we see a lot in Booking.com, something like country and city, we have hundreds of countries and hundreds of thousands of cities. So this introduces multicollinearity, and the thing is estimating a coefficient for every possible city with significant test is difficult, but doing it for country is much reasonable thing to do. So sometimes it's better to stick with small amount of significant results than a large amount of insignificant results. It's a trade-off between predictive power and you know, explainability of the model. I think I need to speed up. Yeah, the root cause for this is hierarchical features tend to be correlated. And the treatment in this case is remove season. We do this, and finally we get to some clustered correlation plot that looks more like the ideal one we saw at the beginning. We see there is blue all over the place. Of course, there are some correlations between some variables. This is fine. In this case, we see the temperature is correlated with June, July, November, with extreme months where temperature goes extreme. And also we see humidity with sunny, with cloudy, yeah, I don't know. Difficult to interpret. Okay, so we get here and we can say that the multicollinearity problem is solved. If you check stats models as we go do this, we see that this condition number that tells you whether there is multicollinearity or not disappears. So stats models give you an alert, and when you get here, the alert goes off. That's a good sign. And now we can also see again the p-values chart, and we can see that there are only 3 variables for which there is a significant result. Every other variable gives you a significant result. And this means we can start now interpreting the model properly and make conclusions. Just for completeness, nothing really shocking in this data set. It's not that interesting. But it looks like fall is the season with the highest demand. I would expect that it was spring or something, but as it turns out, it is fall. Now, humidity and wind have a negative impact on cycling. That's expected, but what I wasn't expecting is humidity has a worse impact than wind. And finally, it looks like these people is business bikers because the demand drops on holidays. And I wasn't sure about this one. I thought, well, I got the sign wrong. And then I go and read the documentation even more closely. And so it seems this is a data set about people that share bicycles to go to the office. So yes, of course, on holidays, people don't go to the office. Some people. I'm at the office. So to wrap up this example, I really need to speed up. A very interesting point, I believe. In this chart, you can see the evolution of the clustered correlation plot when exposed to different scenarios: perfect multicollinearity, redundant variables, hierarchical variables, and no collinearity at all. The percentage shows the percentage of variables that show a significant coefficient, and in the chart you can see the R squared, which is some sort of estimation of the quality of the model from a predictive point of view. So we can see how as soon as we fix the perfect multicollinearity, the R squares improve a lot from really bad to decent, from 0.6 to 0.8, and then it doesn't move at all. Whereas the number of significant variables grows steadily. Of course, there is a diminishing return, but it keeps on growing. So the idea that the message I want to send with this chart is that depending on the purpose of your model, you may want to care more or less about this pathology. For example, if you really care about predictive power, well, you should only probably care about perfect multicollinearity, really severe multicollinearity problems, but maybe not so much about the milder multicollinearity issues. Now, if you really want to explain your model and find correlations, it is important to focus really hard on this problem. And the thing that is general, this is true for every pathology. Depending on the purpose of your model, the pathology that you need to focus to diagnose will be different. Okay. That's it for bicycles. And now let's check this one, business versus leisure. The idea here is to study a little bit about our domain in booking.com. And we want to understand the travel purpose of our visitors. And for this, we have data about users that tell us whether they travel for business or leisure. And we want to build a model that can successfully discriminate these two types of travelers, because we want to give them a personalized experience. It's a completely different website if you go for business or leisure. But in this case, it's completely different scenario than the previous one. Here, I would like to use this reference to a paper by Google, which is called Click-Through Prediction, A View from the Trenches, where they analyze the usage of models in real environment. And that's the case for this model that we have. We want to put it in production and make predictions for every visitor. And the data that is exposed to this model changes all the time. So the view from the trenches looks like this: incomplete information, delayed information, and dynamic information. Incomplete information means we want to predict for every visitor in the website, but we only get labels for people that book and tell us whether they travel for business or leisure. Delayed information means that even for those that book and tell us, they will only tell us 2 or even 15 days later. So we have a delay in the feedback of the prediction. And finally, dynamic information refers to the fact that the label distribution changes. Depending on the season, the proportion of business versus leisure changes, and changes dramatically, and even quite in some sort of a step function. It's not smooth at all. And finally, also the feature space changes. The amount of people that travel from one part of the world or the other changes, the distribution changes, or the anticipation, or how many days you stay in a hotel, it changes. And finally, one that is very, very difficult to work with is extreme cold start. We get new visitors, new users, new hotels. We're growing really fast. We have new destinations every day. And how do we train models that can support this level of madness of the data where they are actually deployed? So the question is, how can we develop a diagnosing tool that helps us to understand whether a classifier, whether a model is doing what it's supposed to do? When in a context we have incomplete, delayed, and dynamic information. So I propose to use this idea of response distribution analysis, and it's amazingly simple and amazingly powerful, at least in my opinion. And the idea is to just build a histogram of the probabilities of the model that the model outputs for every request. So imagine we have 100,000 visitors in an hour, and for every visitor we're going to make a prediction. So the model will output the probability. That gives us 100,000 probabilities, 100,000 numbers between 0 and 1. So we just build a histogram of these numbers. And the structure of this histogram will tell us a lot about what's happening with the model when exposed to the particular context. So this is an example of this model. So in the x-axis, you can see the output of the classifier. That's the probability of the positive class given the feature. Of course, it could be and the feature, depending on whether your model is generative or discriminative. That really doesn't matter. And in the y-axis, you see the normalized frequency of that particular output. So you can see this chart of the probability of an object being, of a visitor being leisure. And this is it. This is the tool. We see in gray the PDF. In orange, we see the cumulative distribution function that, of course, will go all the way to 1. And in blue, you see a recommended threshold that is some sort of threshold probability to decide whether the visitor is business or leisure. Now, let's take a look at different patterns that we find all the time, and I want to analyze how they help us to understand what's happening with the model. The first one actually is what I call an omniscient model. And this is a model that is not only always right, but it knows that he's always right. And what this means is it will never give you a probability. It will always give you 1 or 0. And it's always the correct answer. So if we have such a model, which is absolutely ideal, it doesn't exist, then if we apply this response distribution histogram, then it would look like this. 2 peaks, one at 0, one at 1, and the height of the peaks will be related to the distribution of the classes. This is a 50-50 model because, of course, I hard coded this. I never saw this. And we're never going to see this, but we expect to see this plus noise. We do expect to see some sort of mixture of 2 beta distribution or mixture of 2 chi-square distributions. And we expect to have the 2 modes, one in different extremes. So this is a confused model. This is another pattern. This is a model that is completely failing at discriminating 2 classes. You can see it always predicts pretty much the most common prediction is 0.44, which is very close to some regularized prior. So the model is absolutely failing and using the training data to learn to discriminate into 2 classes. So the main traits of this kind of models are that they have one single mode, it's central, and there is not stable point. No stable point means that if you look at this as a mountain and you drop a ball everywhere in the mountain, the drop will just go away. It won't stabilize anywhere. It doesn't matter what you drop the ball, it will just fall and go. And you'll see why this is important in a second. And the root cause that we always see or suspect about, we cannot really prove this, is that there is high base error. That is that your training set is not really deterministic with respect to the label. That is, you're supposed to use only 2 features, the country of the user and the day of the week. Well, all you can learn is a distribution over the labels. Whether it's business or leisure, you cannot really determine it. So the solution for this is, of course, to add features. And not to create new features from the ones you have. That's not going to help at all. But to add new features, to go and look for more features outside what you already have. If we do that, we might end up with an over-conservative model, which is a model that, again, fails completely to discriminate. But in this case, it's a different, for different reasons. In this case, the model really doesn't achieve to output probabilities, in this case, bigger than 0.52 or something like that. It's very unlikely. And I want to highlight that you may have very good model offline in your computer, running very well, AUC 0.85, but you are probably looking at this model with the biased data set because you can only train the model for these examples for which you have labels. When we put it in production, we need to understand what the model does even when we don't have labels. And that's why it's very common that we see very good models offline and then we put it in production and they don't work. So in this case, the over-conservative model, we have a sparse support. That means not all the possible probabilities are present. It's not smooth at all because it's very shaky. It's more like a nervous model. There are extreme modes. So there is one mode. The most frequent value is very close to 0 or 1. In this case, closer to 0. And there are multiple stable points. Wherever you drop the ball will get stuck. The main potential cause that I've seen for this is the sparse model. So if suppose that you use a feature like hotel ID, if you don't have a weight for every possible hotel ID, then you will see this. Because then when a new, it's not a new hotel ID, but it's just that your model didn't assign a weight to one particular hotel ID, for example, because you're using very strong regularization. But when you put it in production, that hotel ID will appear, and since you don't have any weight, and this happens for many hotels, you will see this type of structures. And the way to fix it is to make sure that you have something to say about every feature value that the model observes when actually serving predictions. In that case, elastic net regularization is much more advisable for machine learning people here. Moving on. We start to do better now. So if we fix this sparsity model, now we get the much better model. We can start to see some sort of discriminative power. In the center, you see the blue line. It's actually separating. The support is quite wide, so it goes all the way from one extreme to the other. It's very smooth, but there is an extreme value. In general, this is a logistic regression. In general, we don't want models to be that certain ever. There's no point on being that certain about the prediction. In this case, we see that there is an extreme mode, so the most common value is 1, and it's, well, just too extreme. It's the only value that actually, picks up pretty much the whole distribution. Now, the reason for this one are plenty, and this is the most common problem we see. Cold start is again there. So if you have in a training set a very not popular hotel, you might assign a big weight to it. But you won't see it in training set because this blends into the million of hotels that we have, and you won't cause any problems. Now that particular hotel suddenly becomes really popular, and it has a very big weight. And therefore, the inner product in the logistic regression blows up, and the sigmoid function goes to 1. And this is what we see here. So that's one of the reasons for this problem. A second reason is outliers. This is very common also. You get some outliers that you didn't see at all in training set, and then they might have very large values. And then again, the inner product blows up, and the sigmoid goes to 1. And the actually most common one is integration issues. You develop a model, for example, using how many, the price in euros of a hotel. But when you put it in production, someone sends the price in Colombian pesos. So this will use completely different scale. And again, you will multiply this number by a weight. And again, this inner product blows up, and you get, the sigmoid will go to 1. So this type of structure really helps us to understand what's going on. One thing that I'm not showing here is that we can dig into every bar, right? So we can go and click, okay, who are these guys that are actually telling us always 1? And you can go and look at the value of the features and really make some more handcrafted analysis and find really insightful things. And finally, we get to a maybe good model. So you can see this model, you can see clearly 2 modes, 2 pretty peaks. It's very smooth. There is a very clear threshold that we can use to discriminate between one class and the other. And there is a stable point. That means if we put the ball somewhere in the distribution, it will fall exactly where the blue line is. And that's probably the best threshold to use to make a hard decision whether the user is business or leisure. And the reason why I say maybe is because this model could be completely wrong. Could be absolutely 0 accuracy. So that means that this tool only helps us to understand what type of problems might be happening. It will never tell you that the model is good. It can only tell you that the model is bad. And, well, this is what I just said. And this is the same model a couple of weeks later. And you can see how it really changed quite a bit. And the distribution changed, and we can see a new mode growing close to the recommended threshold. And this means that when there are changes in the underlying distribution of the thing we want to predict, this tool will capture. And this is very useful for us to when we deploy a model, it works, everything's fine, and after 2 months, then this model can be completely wrong. And this helps us to understand this early enough and to capture issues when we can still fix them. This is too good to be true. I think I saw this one on April 1st. No, but really, this is actually very useful. You will see this actually a lot, and this is usually due to leakage. You're probably leaking the label as a feature. And when this leakage is noisy, it's not perfect leakage, the model won't say 1 or 0. It will still give probabilities, but it will be just too nice. And then you should definitely not trust these ones. And finally, it looks like robots travel for leisure. So we had this robot attack a couple of weeks ago, and the model thinks that the robots travel for leisure, and well, yeah, that. And yeah, it took us a while to figure this one out. And the robots are quite systematic. They don't have a lot of variance, so that helped a lot. So if you are developing robots, make sure you change the variables. And yeah, just one more look at from the trenches, like as I like to say. This response distribution analysis help us a lot in this incomplete, delayed, and dynamic information scenario. And the idea is that incomplete information is addressed with global feedback. We can get feedback from every example we make a prediction, not only those for which we have a label, which is very important. Unfortunately, in booking, most people don't book, so we cannot rely on that to actually understand what our models are doing. Delayed information, again, is addressed by the fact that this is immediate. As long as you start making predictions, you can build this histogram and start understanding whether the model is doing bad or not. And finally, dynamic information. Well, this is very responsive feedback that you get because it changes. It's very sensitive to changes in the distribution, and the line distribution of the context in which the model is deployed. It is a thing to still work with for feature space. It's not really that sensitive to feature space changes, but yeah, we need to work to improve that. Some limitations, of course. It only works for scoring classifiers. If you have a decision tree, this won't help you because decision tree doesn't give you a score, doesn't give you. I mean, a decision tree, not a random forest. I know it's not very common, but it's one case in which you cannot use this tool. And it only detects red flags. It points in the directions of pathologies. It won't tell you exactly what to do. It won't really tell you, hey, you have a overfitting problem, fix it, or decrease lambda. No, it will only help you to say, hey, there's something fishy. There is a very nice technique from the object-oriented programming community, and they call it the bad smells. And there are even papers about this. And then they really look code and they detect bad smells. Well, I think this is a very good metaphor for this tool. It's a tool that helps you to get and pick up bad smells. But then once you get this bad smell, you need to go look further to actually check that there is a problem. And finally, regression, nothing to say about it. This won't help. And ranking is a very interesting problem. We have an extension for multi-class for small amount of classes, but if you go to many classes, this doesn't really help. Okay, some closing remarks, 2 more slides. Industrial remarks. So this is the view from the industry. We saw this sequence of diagnosing tool helping us to move towards a better model. And we saw the same with this other tool. They are all helping us to improve our model continuously. So the idea is that model diagnosis can be seen as an iterative process, especially in the industry, maybe not so much in the academia where you can treat every problem as a unique problem, but in the industry we really get this pipeline of problems, one behind the other. So looking at model diagnosing as an iterative process is very useful. This process is driven by diagnosing tools, and these diagnosing tools are what points us in the direction of what to do next. So I have this, what should I do? Should I focus on overfitting? Should I focus on getting more features? Should I change the algorithm because it's just too simple? And yeah, like I explained in the first example, the ultimate goal is to achieve a purpose that your model is set up for. So explanatory models will require one type of treatment. Predictive modeling will require a different type of treatment. And even in predictive modeling, estimating values is not the same as discriminating or classifying versus regression. It's very important to understand what are we actually trying to achieve with our model, because this is what will drive the type of techniques that we use. And yeah, to finish, if we can come up with a systematic diagnosis process, then we can build up a beautiful continuous improvement process. And this is, again, very relevant for the industry, where we got one model behind the other, and we want to be successful with all of them, or at least the majority. That's all I have. Thank you all, and I'm happy to take questions, comments.